Building upon our understanding of alcohols, we now expand our synthetic toolkit to other essential heteroatomic compounds, ethers, epoxides, and organosulfur compounds. While many synthetic routes exist, this episode focuses on the most common pathways, providing a clear visual summary of how regioselectivity and stereochemistry arise from specific reagents and mechanisms. Section 1. Synthesis of ethers. Ethers are primarily synthesized through either nucleophilic substitution or addition reactions. First, simple symmetric ethers can be prepared through the intermolecular dehydration of alcohols under acidic conditions at relatively low temperatures. In this reaction, two molecules of alcohol combine to form an ether, yielding a water molecule as a byproduct. Because it requires two identical alcohol precursors, this route is primarily utilized for the synthesis of symmetric ethers. When we need to synthesize asymmetric ethers, the Williamson ether synthesis is our classic go-to method. This process is an SN2 reaction between a strong alkoxide nucleophile and an alkyl halide. Here, the choice of substrate is critical. Primary alkyl halides are generally preferred. We must use caution with secondary or tertiary substrates, as E2 elimination quickly becomes the major competing pathway, significantly lowering our ether yield. For alkene starting materials, Alkoxymercuration-Demercuration offers a sophisticated and highly reliable alternative. This pathway follows Markovnikov's rule, adding the alkoxy group to the more substituted carbon. The most significant advantage of this method is that it proceeds via a bridged mercurinium ion intermediate. Because it avoids forming a free carbocation, we can smoothly obtain the desired ethers without any unwanted carbocation rearrangement. Section 2. Synthesis of epoxides. Epoxides are strained three-membered oxygen-containing rings that can be synthesized through several mechanistically distinct pathways. Because of the ring strain, these transformations require precise mechanistic control. The most direct method for preparing an epoxide is the reaction of an alkene with a peroxy acid, such as mCPBA. This reaction proceeds via a concerted mechanism, where all bond-breaking and bond-forming steps occur simultaneously. A crucial feature of this pathway is that it is stereospecific. The original stereochemistry of the starting alkene, whether cis or trans, is preserved in the final epoxide product. Another versatile route begins with halohydrins, which undergo intramolecular SN2 cyclization to form epoxides. In the presence of a strong base, such as sodium hydride, the hydroxyl group is deprotonated to form an alkoxide ion. This internal oxygen then acts as a nucleophile, attacking the adjacent carbon to displace the halide-leaving group in an intramolecular SN2 reaction. For this intramolecular SN2 process to occur efficiently, the reacting groups must adopt a favorable anti-periplanar geometry that enables proper backside attack and orbital alignment during ring closure. Section 3. Synthesis of organosulfur compounds. Sulfur's high nucleophilicity and polarizability make these transformations efficient compared to their oxygen analogs. Let's look at how we synthesize thiols and sulfides. Thiols are prepared through a straightforward SN2 substitution process. By reacting an alkyl halide with an excess of hydrosulfide, we can smoothly introduce the sulfur atom. Thanks to the high polarizability and low solvation energy of sulfur, sulfur nucleophiles often react more readily than their oxygen counterparts. Similarly, Sulfides are prepared through a thiolate-based synthesis that is directly analogous to the Williamson ether synthesis. Here, a thiolate ion acts as a powerful nucleophile to displace a leaving group on an alkyl halide. Because the thiolate ion is a strong nucleophile, this reaction proceeds rapidly under mild conditions to construct asymmetric or symmetric sulfides. Let's take a moment to look at the screen and reflect on what we've learned so far. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.